To get a sense of how the activity coefficient is going to affect the PXY and the TXY diagrams, what I want to do is kind of just discuss qualitatively what the influence of the gammas are going to be. Okay? And so what we'll do is we're going to just conceptually go through what happens as we increase the magnitude of the excess Gibbs energy in the system, which is going to be directly related to that activity coefficient. Okay? And so the first case we'll think about is, once again, if we have an ideal solution. Okay? And so the ideal solution, that excess Gibbs energy is going to be equal to 0. And so our pressure, the partial pressures are just going to be given by the regular version of Raoult's law. P2 sat. Okay? Alright, and so here, if we sketched out the PXY and the TXY diagrams, we would see shapes like this, okay? Where, change this to blue, in the PXY diagram, our curve may look something like this, where at the top is the liquid, the bottom is the volume, and for the liquid line, for an ideal solution, it would be linear, while the vapor line would kind of sag. And that just comes from the math of this equation right here. If you rearranged it, you could have it so that you had it in like a slope form, where you just had all your x terms combined. In fact, actually, let's just go through that now. So P1 sat, that's P2 sat, x1 plus P2 sat. Okay? Right. So now we have it in a line form, where the slope is just the difference between the vapor pressures, and the y-intercept is P2, right? And so in this case, P1 sat is lower than P2 sat, so species 1's the less volatile species. In any case, you would get a negative line in that case. If it was the reverse, where P1 was a more volatile species, you would get a positive line. In any case, for the ideal solution, the liquid line's linear and the vapor line's going to be sagging. In the TXY diagram, we don't get quite the straight line, but essentially we would get that I shape. Right up here is volume, down here is liquid. Okay? All right, and so this is a sketch of what the PXY and the TXY diagrams would look like for the ideal solution. All right, but now let's up the complexity. And now let's consider the case where we now have a small positive non-ideality. And so what that means is that your G excess is going to be greater than 0, but not too big. It's just slightly greater than 0. And so when that happens, if the excess Gibbs energy is positive, what we see, remember, the vapor phase is still an ideal gas mixture. We're only changing or only adding non-idealities to the liquid phase. Okay? And so if G excess is greater than 0, what happens is there is what we call an energy penalty. For mixing in the liquid phase. Right? The two species, the two components in our mixture, when they're in the liquid phase, they actually don't really like mixing together that much. uh, either due to differences in molecular interactions or differences in sizes. Okay? In any case, because they don't actually like mixing together that much in the liquid phase, what happens is this excess Gibbs energy destabilizes the liquid phase and makes that phase window smaller. So the region, the pressure and mole fraction region in which you have a liquid becomes smaller. Okay? So if we compare it to the ideal solution, if we sketched out the PXY diagram for the case where we have a small positive non-ideality, what we would see is that instead of having a linear line here for the liquid line, it would actually cave up a little bit. And so now you can see that there's less of a region in which we have the pure liquid. At the same time, it becomes more favorable for the mixture to be in the vapor phase. And so our vapor window starts to increase. So the liquid region gets smaller and the vapor region gets bigger. And that's also reflected in the TXY diagram as well. So here we had the I shape, but now we'll see that the vapor region is expanding and the liquid region is shrinking. So now we get a more of a crescent shape. Okay, so that's if the non-ideality is positive for some reason. Let's now look at the opposite case. We have a small negative non-ideality. Okay? Alright, and so in the liquid phase, rather than there being a penalty for the two species to mix, it's now actually favorable for the species to mix, and you get, I guess we'll call an energy benefit for mixing in the liquid phase. Okay? And so what this will do is it will expand the liquid phase, and it makes it more likely that the mixture will just be a pure liquid. Okay? Okay, and so rather than shrinking, the liquid phase is now going to expand out, and the vapor phase is going to shrink. Okay. Liquid phase expands out, vapor phase gets smaller. Okay? Alright, and so we looked at the case where, our system is non-ideal, but the non-idealities are relatively small.